What's going on, everybody? That's too much chalk. I've actually, this is my third lecture I want to say today. So yeah, I actually gave a lecture. There's chalk everywhere. I'm just gonna. Okay. Hopefully you're all well. Hopefully you enjoy your spring break, whatever that might have meant. Hopefully it wasn't too bad. Hopefully maybe you even had a little bit of enjoyment, a little bit of relaxation. It's been tough on everybody. It's been tough especially on New York. And hopefully you guys are all safe and all healthy and all well. But spring break is over. It's over today. This is going to be a lecture I'm posting for tomorrow. But it's over today. And it's time to get back into it. So I've been doing a lot of work, and now it's time to jump in and do even more work because Theorem has started again. So yeah, it's been tough. Really hope you're all doing okay, but it's time to jump back into it. You guys know the deal. We're doing the long distance learning thing, and this is how I'm dealing with it. Pre-recording the lectures and giving you a chance to ask me questions, either in the comment section or shooting me an email through Jupiter Grades. That being said, that's what this is about, because I got a few comments on the last lecture. Most people understood what was going on, so I didn't really have any questions per se, but one person mentioned that they had a little bit of trouble with example 8 from the related rates handout. So even though I didn't really intend to talk much more about related rates, I figured I would just go through that example in response to that person. This would count as the Q&A session since I didn't really get any other questions. Don't want to rub my nose because it's chalk and you can't touch my face. Okay, so this will count as the Q&A session, me going over this problem. Right after that, we're going into maximum and minimum values and critical points. Some pretty important stuff. After that, we are going to talk about, I think curve sketching will be the next topic, but we're not going to get to that today. Yeah, which I'll probably talk about asymptotes before I do that. So let's kind of just jump into it because, you know, we kind of only have 50 minutes here. Don't want to go too much over time, so we're going to jump into it. But as always, if you have any concerns, you know how to reach me. That being said, I think moving forward, so hopefully by the time our second test comes around, which at this point is going to be close to the end of the semester, and the final comes around, things are going to be a lot more stable, and they're going to be, I will have more options. In the meantime, quizzes are kind of suspended, but what I would do instead, which I figured might be a good idea, is just like post mock quizzes and post the answers, post the quizzes. You can do the quizzes on your own and see how you do. So that way you can kind of track how you're doing with all this stuff. However, it's not going to count for your grade. It will just be something for you to keep up on. And of course, you should be honest with yourself. And you should, if you take a quiz and you realize that you messed up on some part of the quiz, you might want to ask me a question about that. But other than that, I don't really think I have anything to say besides getting into the lecture and then getting home. So we're going to do problem 8 from the related rates handout, and you guys know about related rates. Hopefully that's what the last couple lectures have been on. There are 6 steps to doing any related rates problem. I have them out in a template here. Hopefully I have enough space to get the problem done because this problem is a little bit hefty. So someone has been having trouble with example 8. So let's do step 1 and let's read the problem, make sure we understand what's going on, and then jump into it. So at noon, ship A is 80 miles west of ship B. At the same time, both ships set sail. Say that 3 times fast. Ship A sails south at a speed of 20 miles per hour, while ship B sails north at a speed of 10 miles per hour. How fast is the distance between the two ships changing at 2 p.m.? So remember, this all starts at noon and they set off at these speeds. how fast is the distance between the ships changing at 2 p.m. if both ships are maintaining a constant speed? Okay, so that's related rates problems. You're told about related quantities, namely the distance ship A and ship B are from a dock, and you're told how fast some things are moving, namely ship A and ship B. You're asked how fast something else is moving, namely the distance between them. That's a classic related rates problem. Let's actually jump into it. So what would the diagram look like here? So we have that ship A is 80 miles west of ship B. So things kind of start out like this. So we have ship A is here, ship B is there. And this is 80 miles. And that's west, that's east, that's north, that's south. Both ships set sail at the same time. Ship A sails south. So ship A starts moving down like that. At 20 miles per hour, ship B sails north. So ship B starts heading up like that at 10. How fast is the distance between them? So what is the distance that we care about? We care about this distance that's between them right here. So here's your current ship B, here's your current ship A. That distance is what we care about. So now, the students was kind of confused about the diagram in particular. I'm pretty sure that once I kind of work through the diagram with you guys, you should know how to pick up from there. I mean, it's been a week of spring break, so probably you'd have to get back into the swing of things, but this will be a good way to jump back into things. Here's how I would go about it. I would start labeling the distances things are traveling. So let's say I label the distance here x. So x is the distance that ship A traveled. Let's say that y is the distance ship B has traveled. And let's say the distance that I care about, the distance between them, call that z. Right? Now, notice here we have right triangles. But the thing is, you probably won't be able to figure out what this length here, the base of these right triangles. So the trick here is actually to create another right triangle on top of this diagram. Namely, just imagine this 80 moved down and look at this big right triangle. So this guy right here is going to be the triangle that we care about. And so that is going to be the diagram for the setup. So let me actually clean this up a little bit. So based on that diagram, so now our diagram is going to look like this. This base is 80, that's a right triangle. Now, remember there was a point here where above that was a distance y, below that was a distance x, so the length, the height of this triangle is x plus y, and the hypotenuse of this triangle is z. So that's our diagram here. It's a right triangle where the hypotenuse is z, and the height is given by x plus y, the base is given by 80, namely 80 miles. Now, what do we know? Well, we know how fast x and y are changing. Now, y is getting larger because b is sailing away. X is also getting larger because a is sailing away, so that we know about dx dt and we know about dy dt. We also know that both need to be positive because they're getting larger. Ship A sails south at a speed of 20, so it's going down at 20. Ship B sails north at a speed of 10, so it's going up at 10. And what do we want? How fast is the distance between them changing? We want dz dt. When, now at this point pause the video and try to tell me when. You should actually know when your x and your y values are a certain value. pause the video, and tell me what the values are. Okay, so if we read carefully, which, step one, read. Ship A is moving at 20 miles per hour. Now, they started moving at noon, and this is talking about at 2 p.m. That's 2 hours later. If you're going 20 miles per hour, how far have you traveled after 2 hours? 40 miles, right? So you're going 20 miles every hour. There have been 2 hours, so you actually traveled 40 miles in those 2 hours. So ship A has traveled, X is 40. Also, Y is 20, because if you're moving at 10 miles per hour, after 2 hours you would have traveled 20 miles. So that's the distance that we want here. And so now we can go into the equation. Pause the video. What's the equation? Pause it. Alright, Pythagoras' theorem is what we're going to use. So we know that z squared is equal to x plus y squared plus 80 squared. That's our equation. Now we are going to we're going to differentiate. That's the fifth step. So 2z dz dt is equal to 2 times x plus y times dx dt plus dy dt. I just use the chain rule. Differentiate the outer function, multiply by the derivative of the inside function. Derivative of 80 squared, it's 0. That's correct. So this is our equation here. I can cancel the 2's from both sides. So I have that. Now I just want to plug in. So this is going to be dz dt is equal to, x plus y dx dt plus dy dt over z. Now, we know our x and y. We can plug those in here. We know our dx dt and our dy dt. Can plug those guys in here. But we do not know our z. So what do we do when we don't know that? Right? So when we're trying to plug in but we don't have all the information, we go back to step 4. Right? That's right. Hopefully you remember that. So from 4, if I plug in x equals 40 and y equals 20, that will give me 60. So z squared is going to be 60 squared plus 80 squared. Okay? So what does that mean for z? Now, I'll give you a hint here. This is also something that I told you about to look out for in the last one, in the last video. A very common thing. What you'd want to do is think of the 60 as something like 3 times 20, and the 80 as 4 times 20. Now, why is that important? Well, it's important because the 3 and the 4 and the fact that you multiplied both by 20, that means this is a 3, 4, 5 triangle. Proportionally, that means that your z squared should look like, 5 times 20 all squared, because of the 3, 4, 5 triangle relationship. So now, pretty much that gives you the fact that your z is 100. And so you go and you plug in. dz dt equals x plus y, which is 60, times dx dt plus dy dt, which is 30, over 100. And 10 cancels into that, 10 cancels into that, 3 6 is 18. So it's 18 miles per hour. Like I said, I don't really care about the units, but if you write down the wrong units, I will mark you down. But if you leave off the units, it's fine. 18 is the answer, which means the distance between them is increasing. It's increasing at a rate of 18 miles per hour. So that's the last problem. That's the last related rates problem that I wanted to do. There were a couple more examples on that handout that I gave you, but this is the last one, which I wrote because someone asked me a question about it. It's the only question that someone asked me recently. So let that satisfy the requirements of the Q&A session. I'll leave that for you to copy, and let's move on with the rest of the lecture. So for the rest of it, well, for a while, what I'm going to do is I'm going to give you some new definitions, introduce some new concepts. We'll probably do some calculations at the end, but for now, I'm just going to tell you about some definitions that you will want to know. I believe this is going to be section 4.2 with no, straight garden. Right. 4.2, max and min values. What we're going to talk about here, the main guys are absolute max and min, as well as local maximums and minimums. We're going to talk about what those guys are. Then we're going to talk about how to actually find them. Today, what we're going to talk about is how to find absolute max and mins. I'll kind of describe to you how to find local max and mins, even though I already have in a previous lecture when we were doing the first derivative test and the second derivative test and the concavity test and all that. I actually told you how to find maximums and minimums. So it's actually exactly the same thing, but we're going to find another kind of maximum and minimum here. Starting out. So let's start out with some definitions. And we'll talk about why these are important later on, but for now, let's just learn what they are and how to actually make calculations about them. F of x is a function. We say f of x has an absolute or global maximum at x naught if f of x naught is greater than or equal to f of x talk about on an interval on I. This here is an interval. So f has an absolute maximum on I at x naught if the output at x naught, the y value, is larger than or equal to every other y value for all x in I. So that means that f of x has a global maximum on I. So it's global and absolute in the sense that it's true for all x values in that region on the interval that you care about. Similarly, f of x has a absolute or global minimum on I if at x naught if our f of x naught is less than or equal to f of x for all x in I. I'm going to illustrate what these mean in a little bit, but I'll give you some time to copy that down. Pause, 3, 2, 1, and let's actually move on. We say f of x has a local or sometimes we call it relative maximum on I if this is true for all x near x naught. So by near, I just mean in a small window around x naught. Pretend that x naught is in the middle of some window. If you open up a small distance to the left and to the right, it is going to be the highest point in that small little local region. Similarly, has a local or relative minimum if f of x naught is less than or equal to x for all x near x naught, near being the close operative word here. So pause the video, make sure you copy that down, and we are going to move forward in 3, 2, 1. So that's the difference between global and local maximums and minimums, which most of the time I'm going to use the phrase absolute maximum and minimum as well as local maximum and minimum. So those are probably, so all the words I wrote down, these guys are very commonly used. Personally, I like to use the words absolute and local. So I'm going to talk about what these guys are pretty soon, illustrate the difference between the two so you can actually see it, draw some pictures and stuff. But before, I just want to make another vocabulary word here. Max and min points are sometimes referred to as extreme points. And the plural of which is extrema. Okay, so this might be a word or a phrase that I will use sometimes, or your textbook might use. I want you to know what it means. So, for example, if I say absolute extrema, it's the same as me saying absolute maximums and minimums. Right? So an extreme point can be a maximum or a minimum point. We just refer to all of them as extreme points. So if I talk about absolute extrema, or find all the absolute extreme points, I'm talking about the maximum and minimum points. So you should notice that. And I'll give you some time to pause the video to copy that down. But we are going to keep moving. So, yeah, another vocabulary. Let's actually just do some illustrations here. some graphical examples for you to see what I'm talking about. Some A, B. Filled in, that's A, B. So what I'm going to want us to do is to identify all extrema, absolute and local, on these pictures that I'm drawing, so you can actually talk about the difference, or you can see the differences between the two. I do not know what just happened. I did not touch the buttons for the screen. It's pretty late. I guess this is when the building gets haunted. I think that's all the examples we want to do. So here's how we're going to do it. Let's give a key here. Let's say AM is absolute max. Let's say little am is absolute min. Let's say LM is local max. Little lm is local min. So we're going to go through these graphs. We're going to pick out all these guys. Now, what you might want to do is pause the video. It shouldn't actually take you that long. Read the definitions that we wrote down, pause the video, and actually try to fill in what these points are. So I'll give you a pause in 3, 2, 1. Now hopefully you kind of fill these things out, and we can hopefully see if your answers actually coincide with mine. Now, in the first example, where would you identify the absolute max and min? Well, hopefully you'll notice that an absolute maximum would occur at the peak here. That's an AM. The absolute minimum is the smallest one if I'm thinking of extrema on AB. So if that wasn't clear, now pause the video and do them. Okay, so now here, these are absolute minimums, little am, little am. So on the interval AB, these are the smallest values on that interval. That's by definition is our local minimum, our absolute minimum. This is the largest value on the interval. Now, you might notice that even if we look locally, it turns out that this is also a local max. And these guys are also local minimums. That being said, if you're looking at a point that is both an absolute and a local, usually, not always, but usually what you're going to do is the absolute supersedes the local. So if you had to identify these points to be one thing, you'll probably identify them by what's in green as opposed to what's in red. Of course, this all depends on the context. When it comes to the next section that we're going to be doing, or the next 2 sections later, when we're talking about curve sketching, it might actually be more important for you to identify the local guys than the absolute guys. But in general, the absolute extrema take precedence. Right. In this example, hopefully you've discovered that this guy here is an absolute max. It's also a local max. And this guy here is your absolute min, and it's also a local min. If you look at this guy here, you'll notice that there is a local minimum here and an absolute minimum. And it will turn out that, where is the absolute maximum? This one has there's no absolute max or local max. Notice that there is no y value here on the interval AB that is larger than or equal to every other y value, because this keeps going up. It keeps getting higher and higher and higher, which means any value you tell me, eventually there's a y value larger than that. And so there's no absolute max and min. If you look at this one, you'll notice that there are no extrema. So this guy, the fact that he keeps going up tells you that there is no biggest y value, not in any sense here. In this case as well, because this keeps going down, there's no smallest y value. So that's that. So that has no extrema to it. Hopefully you figured that out. If you look at this one down here, you will notice that we have local minimums here, 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 and here. You will notice that we have local maximums here, here, and here. You'll also notice absolutes. So this here is also an absolute minimum. That's probably what I would think about it. This one here is an absolute maximum. But all the other guys are local. So this one will show you the difference between the two, because you'll notice that we have both being represented here. Notice that these two guys here are local maximums, but they're not absolute maximums. Why? Because if I look in the small local region, those guys are going to be at the tops of the hills, right? So if you look on the entire interval, they're not the biggest guy around. But if you look at their little small pond, and their little plot of earth, they are the king of the hill. That happens here, here, and here, right? Now if you look globally across the entire interval, this guy is the biggest along the entire interval. Globally, he is the biggest, so he is the absolute maximum. Similarly, locally, all of these guys are the smallest. If you look in their little window, they're the smallest guy around. But however, if you look on the entire interval, this guy is the smallest, so he gets deemed the absolute minimum, whereas all these other guys get deemed the local minimum. Now, if we're looking at this example, what do you think here? Tell me about a local max or a local min. Let's go local first. So here's a local max. If I look at that, in that little window, he's the biggest guy. There is actually no other local max. Now you might think there are a couple situations in which students might make a mistake here. Some people might identify this guy as a local max or an absolute max probably, but it's important to know that that's not shaded, which means that point is actually not in the graph, which means this graph keeps increasing to that point, but it never actually makes it to that point. So this point actually does not exist on the graph, so it's nothing. It's nothing. Now you might say, locally, is this guy, this bulb right here, is he the highest guy on his hill? Well, the answer is no, because if you were to open a window to the left and to the right, on the left, immediately to his left, there are y values on our function that are larger than him. So he's not a maximum either, not in the local sense or an absolute sense. Here we have a local minimum, but we do not have any absolute extrema. There is no absolute max, and there's no absolute min here. Right. So that is, hopefully that gives you some intuition. When it comes to local, you're looking at just a small window around that part of the function, and who is the biggest or smallest guy in that small window. When you're talking about absolute max and mins, you're looking on an entire, some large scale. You're looking globally across a very large scale and see who is the biggest on that entire interval, or who's the smallest on that entire interval. Right, so hopefully that gives you some appreciation for what absolute extrema are and what local extrema are. Now, in my 1206 class, I would actually, well, the first thing I'm not going to, I wouldn't prove even in that class. The second thing I would actually prove in that class. But there are some important theorems to know here when it comes down to all this extrema business. Now, clearly, I've been given examples ever since we started talking about derivatives, and we actually looked at the first derivative test and the second derivative test and concavity and things like that, of why it might be important to identify maximums and minimums on a graph, right? The graph itself is not important. What the graph represents is important. So if it's like profit or cost or something like that, you'd want to know, where am I seeing the highest profits or the minimum profits? Or if it's, you know, like the size of a tumor, like in that example, you want to know, when was it the biggest, when is it the smallest, what was going on around that time. So there are some concepts that you'd want to know about, because knowing that finding maximums and minimums, whether they're absolute or local, is a very important thing. We're going to want to know how to find them. How do you go about finding them, especially if, yes, we know about finding them for very simple graphs, like if I use y equals x squared. We all know there is a minimum at the origin, and so on and so forth. But what if it's a more complicated graph? How do you go about actually finding out where these guys occur? And to that end, there are some important concepts, some important theorems that you should know. First important theorem is called the extreme value theorem. Now, there are a couple ways to look at the extreme value theorem. Some people actually take this as an axiom, meaning it's a mathematical statement that is self-evident. We don't prove it. We just assume it's true. Some people actually don't assume it's an axiom, and they actually prove it from other things. But those tend to be way beyond Calculus 1 level. So I'm just going to state the extreme value theorem for you. I'm not going to prove it. And it says the following. If f of x is continuous on AB, then f of x attains its absolute max and its absolute min on AB. In other words, the extreme value theorem is a very important theorem. It tells us the following, and there are a lot of things that we use the extreme value theorem to prove. It's not even funny. It's a very simple idea. The idea is the following. If you have a continuous function on a closed interval, then the function is guaranteed to have both an absolute max and an absolute min on that interval. If you look back at the examples that I did earlier, you will notice in the cases where I said there was no absolute max or min, why was that the case? You will notice that on the interval AB, the function was not continuous. It actually shot off to infinity, or there was a hole, or something like that had to happen. Once your function has to actually exist in that interval, right? So like between A and B, there's a point, it's going to take on values at A and B, and then it continuously takes on values in between them. There is going to be a point in there where there is going to be a highest value and a lowest value. It will not shoot off to infinity or down to negative infinity, and it won't have gaps, so you'll always be able to attain a maximum or a minimum, right? That is called the extreme value theorem. There are times in test where I've asked the question, oh, here's a function, and the function is like a polynomial or something. Find the absolute max and min, and students have actually written as an answer, oh, this thing has no absolute max and min. And when they write that, I know they have no idea what they're talking about, because I definitely mentioned this theorem in any Calc 1 class that I teach, and it tells us that a continuous function will always have an absolute max and min on any closed interval that you pick. So if I ask you about absolute max and min and it's a continuous function on a closed interval, which is the only situation that I'm going to actually ask you about an absolute max and min, by the way, then it is guaranteed to have an absolute max and min. So if you conclude that there is none, you made a mistake, and you should know that you made a mistake. So extreme value theorem, very important theorem. It's the theorem that tells us we're guaranteed to be able to find absolute max and minimums in this situation. If you're a continuous and you're continuous on this closed interval, then somewhere on that interval, you will attain a y value that's larger than or equal to every other y value, or you will attain and you will also attain a y value that's smaller than or equal to every other y value, right? This will have to happen once you're a continuous function. So that's the very first important concept, theorem that you should know. So this is going to tell us that there will always be an answer in terms of global extrema for continuous functions on closed intervals. The other, I don't know if I can fit here. The second important thing that you're going to want to know is something what's called Fermat's theorem. Now, this does not refer to Fermat's last theorem. Some of you might know about that. There was a very popular theorem called Fermat's theorem, Fermat's last theorem. It's called the last theorem because Fermat was like, hey, I discovered this really cool theorem, but he never proved it. He just wrote it in the margin of his textbook, and he was like, hey, I discovered this really cool theorem, but you know, the proof is too long for me to write in these margins, so that's that, right? And it drove mathematicians crazy for a long time, more than 300 years, kind of long time. And a mathematician called by the name of Andrew Wiles, of course there's a whole story about it, it wasn't just Andrew Wiles, but he's the guy whose name everyone just noticed was was this. He kind of proves something that has Fermat's theorem as a special case. You can actually use it to prove Fermat's last theorem. But it was a theorem that basically says, well, we all know Pythagoras' theorem, right? A squared plus b squared equals c squared. And we know that there are numbers that can go with this, like 3, 4, 5, right? 3, 4, and 5. So now the question is, if you make this different powers, like n, where your n is larger than 2, then it turns out that this, there is no positive integer values A, B, C that solve this equation. Right? That was Fermat's last theorem, and it actually took mathematicians 300 plus years to prove. Was proved in the mid to late 90s, I want to say, by Andrew Wiles. He actually proved something else, but this theorem actually follows directly from what he proved. I'm not talking about that theorem, but the same guy who came up with that theorem, or who claimed to prove it, some people don't even believe he actually proved it, had another theorem. And this is the theorem that he has. This is called Fermat's theorem. There are a lot of other theorems by Fermat. Some called, there's Fermat's little theorem, you have Fermat's last theorem, you have Fermat's theorem. Like, there are a lot of things named after this guy. Fermat, he did a lot of important things. Anyway, Fermat's theorem, when people mention that, what they're talking about is the following. Suppose f of x attains an local max or min at x equals x naught. So there is, at some x value, your function hits a maximum or a minimum. Then, and f prime of x exists. So this is the derivative of the function. Exists at x naught. Meaning, if you find the limit, the derivative limit, and plug in the number x naught, it will actually work out. Or you do the derivative via some shortcut formula and plug in x naught, it's actually a number that makes sense. Then, f prime of x equals 0. So that's Fermat's theorem. It says if a function is known to have a maximum or a minimum, and the derivative exists where the maximum and the derivative and the minimum is, then at that point the derivative must be 0. Meaning, you can have the function behaving like this. That's a maximum. If the derivative exists, it's not a sharp corner, it's not undefined, it's not something crazy like that will cause the derivative to not exist that I spoke about. Then the tangent line to the curve at that point will have slope 0. Similarly, if it's a minimum, the tangent line at that point will have slope 0. As long as the derivative exists, as long as you can draw a tangent line, the slope of the tangent line will be 0 at a maximum or a minimum. This is Fermat's theorem. Now, there are certain, did I mention that here? Let's talk about some important facts with Fermat's theorem. In fact, let's talk about what it does not say. That's what it says. Here's what it does not say. The converse is not true. Meaning, if I know that f prime at some point equals 0, it does not mean we have a max or min there. Right? if I know there's a max or min and the derivative exists, I know that the derivative should be 0. But knowing that the derivative is 0 is not going to guarantee a max or min. Here's an example. Y equals x cubed. Right? Let's call that f of x equals x cubed. Notice here, f prime of x equals 3x squared, and f prime at 0 will equal 0. But are you a maximum or a minimum at 0? The answer is no. We all know how x cubed looks. It looks like that. There is no max or min at x0. Right? So, knowing that the derivative is 0 does not guarantee that you have a maximum or a minimum. So, that's important. So, it's like, knowing that you have a maximum or a minimum and the derivative works out, you know that the derivative has to be 0, but knowing that the derivative is 0 does not mean that you're going to have a maximum or a minimum working out. Here's another thing. When the derivative does not exist, you can have either a max or a min. So another note. We can have extrema when the derivative does not exist. It's another thing you can notice. Now, some of you might be able to give me an example here. Can anyone think about an example? I'll give you the typical one. F of x equals absolute value of x, right? So this is a function that we know looks like a v. Now, there have been a couple times throughout this course where we proved that it does not have a derivative here, but it's a minimum. So this guy here is an absolute minimum. And it's a local minimum. But f prime of 0 does not exist. So we have a minimum at 0, but the derivative does not exist at 0. So here's the thing. Fermat's theorem tells us when max and mins occur, the derivative is 0, provided it exists. However, we do not have a guarantee of what will happen if a derivative does not exist. The function cannot exist and it might not have a max or a min, but it's also possible for the derivative to not exist, and you do have a max or a min. It's also possible that 0, you can have a derivative that gives you 0, but you don't have a max or a min. So putting this together, what does that mean? First of all, knowing where a derivative is 0 might be worth checking out anyway, because you can just do a test. If you identify all the points where the derivative is 0, you can just check afterwards, is it a max or a min? So it might be a good place to look at, as is suggestive by Fermat's theorem, even though we can't directly use Fermat's theorem. Also, knowing where a derivative does not exist, knowing about examples like this guy, the absolute value of x, we know that, at points where it do not exist, we can have sharp corners that are maximums and minimums. So we might also care about points where the derivative does not exist. So we get the following idea. If we want to figure out where extrema points are, where are the extrema? Where are the local and absolute extrema? There are two places that we're going to want to check out. They are suggested by Fermat's theorem and the negations of Fermat's theorem. One, we want to find all points where the derivative is 0, specifically 0. And two, we'd want to find all the points where the derivative does not exist. These 2 points are going to be prime candidates for where a max or a minimum might show up. There's no guarantee, but there's a chance that it might show up in these situations. So these 2 ideas lead us to the idea of identifying points where the derivative is 0 or undefined. And it is critical that we can identify these points when it comes to identifying maximums and minimum points. So what do you think a math person calls it when it's critical to find that point? We call it critical points. So, definition. X is called a critical number of a function f of x if f prime of x equals 0 or f prime of x is undefined. So that is the definition of what we call a critical number. Now, sometimes that is called a critical point. I'll make a note of that in a little bit. The point, if x is a critical number, the point x comma f of x is called a critical point. So this is the critical number, and this is what's called a critical point. And I might also say, colloquially, I just realized I don't remember how to spell the word colloquially. But I'm a math teacher, okay? Not an English teacher. In practice, we sometimes call critical numbers critical points. So, there might be times when you'll hear me or some other math person say, oh, x equals 5 is a critical point. Technically speaking, it's not correct to say this, but everyone kind of knows what you mean when you do say it. It means that at the point where x equals 5, that coordinate is going to be a critical point, meaning plugging in x into the derivative is either going to give you 0 or it's going to give you an undefined value, right? So in practice, we might call it critical point. But it is actually sometimes the critical number. So they might refer to the x value as a critical point, which technically is not, but everyone will know what you're talking about when you do say. But that's what a critical number is and what a critical point is. Let's see, how much time do we have? Oh wow, we're actually over time. Okay, let's wrap up there, I guess. So tomorrow, well, I'm posting this for the lecture tomorrow, so I guess maybe it's going to be Wednesday. Whatever. In the next lecture, we're going to move on. We're going to talk about how to identify absolute maximum and minimums using critical points. We're not going to actually talk about right now identifying local maximums and minimums by critical points, because one, I actually already told you how to do this, even though I didn't really tell you what I was doing at the time. I didn't really use the phrase critical points, I don't think. So we actually know how to find local maximums and minimums. We use that, the first derivative test. You could figure out maximums and minimums from that, which we covered a few lectures ago. I don't remember how many lectures ago. I'm going to tell you how to identify absolute extrema using the closed interval method. We'll do some examples there, and then we'll jump right into curve sketching. Didn't realize we were over time, sorry about that. I will wrap things up right now. Hopefully you guys are all good, hopefully you guys are all safe. If you have any questions, leave them in the comment section or email me through Jupiter Grades, and I will get back to you. Stay safe, stay happy, stay healthy, and keep studying. Ciao.